Legacy astrophysics relies on continuous central force calculus to map the movement of the planets. These models, such as Kerr black hole ray tracing, successfully capture macroscopic closed loops, yet they treat spacetime as a completely smooth manifold. This approach erases the discrete mechanical structures operating beneath the surface. We can find those structures in the Jet Propulsion Laboratory's 3,000-node dataset. To see them, we have to ignore the traditional 2D elliptical lines we've been taught to expect. Without the orbital rendering, the raw spatial binary floats appear as a chaotic point cloud. But a shift in perspective reveals highly structured, overlapping concentric rings. This geometry becomes visible when we process these coordinates as a mechanical equilibrium system. Stripping away the assumption of curved spacetime allows the raw data to reveal a different geometric architecture hidden in plain sight. This process begins by removing Newton's gravitational constant and dark matter mass estimates from the dataset entirely. In place of gravity, we feed pure 3D velocity vectors into a hydrodynamics framework using the dynamic pressure equation. This allows the system to be treated as a pure fluid phase mechanic environment. Localized pressure differentials emerge across the medium, generated solely by kinetic motion. In this framework, orbital paths represent energy navigating pressure gradients rather than bodies falling through curved space. Without gravitational assumptions, the heliosphere resolves mathematically as a pressurized fluid mechanical cavity. This 1861 photograph captures the turbulent surface of the Sun, which functions in this model as a kinetic impeller driving the system's outward pressure. This solar impeller blasts electrons and protons outward at energies typically between 1.5 and 10 kiloelectron volts. Driven by coronal temperatures and magnetic fields, this flow reaches velocities as high as 900 kilometers per second. As these particle vectors radiate outward, they encounter the universal squeeze, the ambient matrix pressure of space pushing inward. We use the cavitation formula to calculate the equilibrium point where the impeller's output meets the substrate's resistance. This boundary forms the heliosphere, a bubble-like rigid confinement shell surrounding the solar system. Because the galactic system is moving through the substrate, this boundary creates high laminar shear as it travels. The heliosphere acts as a pressurized cage, dictating the fundamental boundary conditions for all internal kinetic energy. This creates a mechanical problem. A flat 2D orbital trajectory cannot maintain momentum when locked inside a pressurized spherical boundary. Standard flat orbital planes become physically impossible in this environment. The 3D confinement shell forces them to buckle and fold. The mechanical solution to this confinement is found in 3D Clelian spherical curves. A Clelian curve constrains motion so that the longitude is directly proportional to the polar angle. This proportional constraint forces the trajectory to constantly precess and fold back on itself. The macroscopic outcome is a continuous figure-8 hourglass loop that wraps around a central node. This figure-8 is the mandatory physical geometry for a standing wave balancing spatial momentum inside a pressurized cavity. The movement of the pressure boundary creates localized pressure drops, which naturally spin off frictionless cavitation side eddies. Fluid movement within the matrix forces chaotic stellar material into high-pressure standing wave nodes, which align perfectly with the JPL dataset. Planetary bodies sit at these acoustic Russell nodes within the matrix. If we track the energy flow to the primary distal node on the far side of the figure-8, directly opposite the Sun, we find a specific structural anchor. This distal anchor point is Jupiter. Jupiter provides the bulk modulus resistance required to stabilize the Sun's output, functioning as the primary static equilibrium bubble for the entire system. The Sun and Jupiter act as opposing anchor nodes that lock the primary tension lines of the heliospheric cavitation current into place. This mechanical reality extends to Earth, which sits precisely within one of these localized acoustic pressure nodes. When the broader galactic medium's equilibrium field shifts, it creates a phenomenon known as substrate nodal drift. A tilt in the node subjects the entire planetary container to directional shear and an immediate pressure gradient. Earth's fluid ocean layer acts as the most sensitive indicator of this drift, flowing instantly to re-establish spatial equilibrium. These regional ocean displacements and pressure spikes are mechanical responses to the shifting fluid matrix, rather than external gravitational pulls. When we zoom out, we see a system of rotational kinetics governed by inertia and angular momentum, where energy and mass are locked into a fluid mechanical balance. The architecture of our cosmos is a continuously cycling, highly structured figure-8 cavitation current, bounded by pressure and anchored by kinetic nodes.